Hi, I'm Thales Silva from the University of Campinas, and I'm going to present our work, Learning from Memory, Non-Parametric Memory Augmented Self-Supervised Learning of Visual Features. This is a joint work with Professors Elio Pedrini and Adrian Ramirez. Self-supervised learning has become the horsepower of deep learning. From transformer-based generative models such as LLMs or diffusion models to large retrieval-based systems, these techniques rely on self-supervised learning as a way to scale the training of neural networks to extensive data collections. In the context of learning representations from images, there is a rich diversity of self-supervised learning methods, each with its unique approach, benefits, and drawbacks. Some of the most popular approaches to SSL include the family of embedding prediction methods, the family based on signal reconstruction, and the family based on clustering. These methods can be contrastive or non-contrastive, may have Siamese or non-Siamese architectures, employ a momentum encoder, or a combination of these. Among those methods, the clustering approach to SSL achieves state-of-the-art performance on downstream tasks using frozen features. In the context of SSL, this approach to learning representations works by discretizing the embedding space into a set of prototypes, which are used as anchors to optimize the input views of an image. While clustering-based methods show promising downstream performance, they pose a significant challenge in training, primarily due to their high predisposition to collapsing the representations to trivial states, which current methods try to avoid by using explicit regularizers and hacks that introduce strong priors and stabilize learning. Based on empirical evidence, our research suggests that the difficulties in training clustering-based SSL methods arise from learning the prototypes from scratch using SGD. To address this problem, we propose an alternative non-parametric solution that improves training stability and final downstream performance. We remove the learnable prototype layer from clustering-based methods and introduce a memory component that stores representations from previously seen images during training, posing the representation learning problem in terms of learning by remembering. Intuitively, when learning a new concept, we constantly compare what we see with what we already know in order to gain insights and create new analogies. For instance, when a new concept is presented to us, we tend to be more surprised or impressed by first knowing about it. However, when that concept is presented a second time, our level of surprise tends to be much smaller because we already have an internal representation of that concept in memory and we can refer back to it to make sense of what we are seeing. A learning framework begins generating multiple views from an image using data augmentations. Each view is forwarded through an embedded transformer encoder that projects the image into a low-dimensional representation vector. The learning framework contains a memory component that stores representations from previous training iterations. From the memory, we randomly sample a smaller memory block, which is used to optimize the views for consistency. At every training step, we compare the current signal being perceived, in this case the two views of the Shiba dog, with a subset of representations in memory. Intuitively, if the neural network learns good representations for different concepts in a dataset, we expect the two views of the same image to activate similar regions in memory. Moreover, the activated regions should represent concepts similar to those currently perceived. In other words, the representations from the views of the Shiba dog should strongly activate the region in memory represented by the image of the black dog stored in memory. Lastly, we update the memory with the representations of the current signal and repeat the process. We validate the representations learned by our method on many downstream protocols across many datasets. The downstream evaluations include transfer learning, image retrieval, copy detection, low shot classification, robustness, and more. Overall, our method learns transferable strong representations in a stable training framework, avoiding extra regularizers and additional hacks to avoid mode collapse. Check out our paper and code on GitHub.